Hi everyone, I'm GKCS. We are talking about the second part of Barron's awesomes now. So in the last part we saw how we came to this conclusion that for any S of I, we can find the range for which the corresponding S of J's will be. Alright, if you haven't seen the first part, you definitely should because these won't be making any sense otherwise. And for every bth bit, we are actually doing this. Okay, so I haven't actually written the comma b plus 1 and stuff like that because this is for every bth bit. Now, what we need to do to answer these queries is have a range data structure. So one of the data structures which I spoke about was segment trees, and I'm very comfortable with it, but in this particular problem, I would probably prefer to use something like a binary index tree, a BIT or a Fenwick tree, other names for that. The reason for this is because this problem has a reasonable space complexity asked. So order of sum of all elements. Is the space complexity to answer these range queries. And if we have a segment tree, that could be as large as, well, the size of n is 10 raised to the power 5 into 3. The size of each element is at most 50. So multiplying those two, we get 10 raised to the power 7 into 1.5. I'm trying to find out what is the maximum space that will be required by the segment tree. So this is going to be 16 into 10 raised to the power 6, which will be the next power of 2. So I'll take that as 1.6 now. And then twice of that for the segment tree, construction of the entire segment tree. So that is 3.2. And then each element is at most 8 byte long, 8 bytes space, because I'm going to be storing a long. That will be the value in each segment tree node. So that would be 225 by 0.6, yeah, into 10 raised to the power 7. So that is 2.56 into 10 raised to the power 8. So that is 256 MB of memory. Okay, this is a lot. 256 MB is maybe enough, but it's pushing the limit a little bit. So what I would like to do, also because I haven't ever tried a binary index tree, is to use a binary index tree here. Not only are the space requirements a little lesser, it's also a little faster in terms of querying and updating. Alright, the only problem with binary index tree, as we'll see, is that you can only do cumulative operations. Let's have a look about what I'm talking about. So I won't be going into too much detail about the implementation of BIT. I can probably do that in a separate video, but if you don't like BITs at all and you like segment trees, you can have a look at that video. What I'm going to do is I'm just going to take an example and have a look about how things go. So this is the array we are playing with, right? Initially we have this array. We have taken the bit index to be 2. So we'll do this for all indexes, but we are doing it for a single index now. Bit index is 2. So you see that we have moduloed with 2 raised to the power 2 all the values. And this is what we have in the end. Then we take the prefix sums. So this is S of I and the S of J that we are talking about, right? So over here also we are going on taking with modulo 2 raised to the power 2. So this should have been 9, 1 plus 4 plus 4, but it got moduloed and became 1. Let's see how the binary index tree will happen. Firstly, in the BIT, the first node is worthless. So it's 0 and it has the index 0. Okay, the second node has an index of 1, third node 2, the fourth node 4, the fifth node 8, and so on and so forth. All powers of 2 come as children of the first node. The first, I mean the root node basically. So these are nodes of the root. Fine, what else can we say? 2 has parents. So in fact, this is not how we construct the tree. What we do is we come to index 3 and we see what is the parent of 3. So index 3 is somewhere over here. And we see that its parent is the rightmost bit when it is flipped. Okay, so this becomes 3. Boom. What about 4? 4 has children of 5 and 6. I just write that with the blue marker, that's alright. 5 and 6. 6 has a child of 7. Okay, and 8, we don't really need to go that far because the indexes here are within 5. So actually, I don't need to go that far. Okay. So the value here, this needs to be, the values here need to be updated. We need to actually construct and manipulate with the answers with this tree. So firstly, you get a value of 1. So S of I is equal to 1. Now you remember the two constraints that we had. That is, of course we should write that down. S of j belongs to either S of I plus 2 raised to power b or S of I plus 2 raised to power b plus 1. So this is the first range. Union with S of, these are two disjoint sets of course like we said, I minus 2 raised to power b plus 1, comma S of I. So this is what we are playing with, right? S of I is 1. So the two ranges that we have effectively are 1 plus 2 raised to power 2, which is 4. So 1 plus 4, which is 5, and 2 raised to power b plus 1, which is 8. So 1 plus 8, which is 9. So this is one range that we have. And I think, yeah, this is including 5. The other range was exclusive entirely, and we had S of I minus 4. So minus 3, should we take that? No, not really, because the sum value won't ever hit negative. That much is guaranteed. What about this? So minus 3, I've taken it as 0, because that's as good as ignoring those ranges. S of I is 1. So 0 is not counted, 1 is not counted. The only, it's a null set, so you don't need to take care of this. But yeah, your program it'll check for those two ranges whether they're inside this or not. So this will be 1, 0 after your program converts them to the right numbers, right? So this is the interesting range. This is effectively from 5 to 8, inclusive, both. 5 to 8. Right. We need to find all numbers in 5 to 8. Firstly, we need to construct this BIT. So 1 has to be updated by a value of 1. So let's do that. 1 has to be updated by a value of 1. Value 1, meaning the index 1 plus 1. Okay, because the first node is redundant, we need to add 1 to whatever value we are trying to update. Okay, this is a quirky thing about BIT, but effective index is 2, and so you're trying to update the value at 2. By what? Because the frequency has gone up by 1, we are updating it by 1. So f of 1 has to be updated, and index is then 2 in the BIT. So we go to 2, we add 1 to it. That's reasonable. Everything is 0, so this becomes 1. What's next? The next node has a particular formula by which you can calculate it. Alright, let's do that. Oh, I think I just lost the range here. But yeah, it was 5 to 8. So I'll just keep that in mind. Okay, next node from 2. 2 is index. Index is 2, alright. And you need to take the 2's complement of this, which is plus 1. Negation plus 1. These are all procedures that you need to do to understand a binary index tree, alright? The next node is going to be 4, I already know, but yeah. Then you have AND with the index, whichever number, and then all you need to do is add the original number to that. So this is the order 1 operation that you need to perform. Okay. 2 is the index that you have. So not of 2 is everything 0 except the second bit being 0. Everything 1 except the second bit being 0. So this is 0, lots of 1s, and this is what you're left with. You add 1 to that, you're effectively making this 1, 0. And that with 2, lots of zeros here. So this comes out to be lots of zeros and 1 0. So that is 2. 2 plus 2 gives you 4. So like I said, next node that we need to update is 4. So what value is added here? 1. 0 plus 1 again becomes 4. And after 4, you will get 8 if you follow the same procedure. So we are going to be ignoring that because that's out of our range, right? 5 is the maximum range that we have. So, cool. What about the next node? 5. 5, like we said, because of the BIT stuff, 5 has an index of 6. 5 plus 1. Sorry. 5 plus 1 becomes 6. 6 is the index that we're looking at. Not of 6 is going to give you 1, 1, 0. Not of that is going to give you lots of 1s, 2 zeros, and a 1. So this is the not of 6. This is 6 itself. So first of all, with not of 6, we need to add 1 to it. So this becomes 1, 0, and this number. So we AND 6 with 2's complement. This is in fact 2, right? Because yeah, everything else is 0 except this thing. So 1, 0, which is 2. 2 plus 6 is what you need to take care of, which is a little weird, but okay. We have 8 which needs to be taken care of. So first of all, 5, of course, 6 is where we need to go. We update that by 1. 8 is not what we need to take care of, but we don't care because it's out of our range. So that's fine. Nothing to do. 1 again. 1 comes in again. We say the same procedure. 1 is updated to 2, and over here also 1 is updated to 2. These 2 indexes are updated. 1 again. Same procedure. Thank God for that. Because the binary index tree is a little funny, the way it behaves, but it works quite well. Sometimes. You have 2 here. So 2 has an effective index of 3, like we said. 2 plus 1 is 3. This is the negation of 3. So 3 negated gives you 1, 0, 0. Last 2 indexes are 0. Now add 1 to this and you get this number. So plus 1. Now if you AND that with 3, then you get this number here, and that's also coming out to be 2. Weird. 2 plus 3 gives you 5. Right, so initially, of course, I keep forgetting this, but we go and updated that value. So that's equal to 1 now, isn't it? Yeah, this thing has made this value 1. What we then did is go to index 5 and update that also. So add 1 to that. 0 plus 1. What's next? After 5, 5 becomes effective index of, no, 5 doesn't become effective index. 5 is the node that we need to find the next update from. So 5, not of 5 is not of this number. So that's equal to lots of zeros here is what 5 is. Not of 5 is going to be lots of 1s and a 0, 1, 0. Plus 1 to that is going to be this number, and you AND these two to get 1. Okay, so this is what we have 1. 1 plus 5 gives you 6. So we need to update 6, which is whatever value was here 1 plus 1. So finally we have found a common node which is having value 2 now. Okay, and 3, what possibly can 3 do? Well, 3 is going to have 1, 1 here. Weird, isn't it? 3 is going to have 1, 1 here. When did we ever come across 3? Did we ever come across 3? We shouldn't have. Then why haven't we taken the not of 3? Well, From what I can see, why did I end with 6 then? Or maybe I'm getting really confused. Let's just do this for 3 and figure out what happens. This is 5, right? 5 got updated by 1. Alright. No, 5 became 6, yeah. And 2 became 3, yeah. This is where things get really confusing, because 3 has an effective index of 4. So 3 has an effective index of 4, which means this node has to be updated. So that becomes, from 3 it becomes plus 1. So this becomes effectively 4. Stupid effective index. Really, but maybe some people find it easy to understand, but I find BITs, yeah, that's enough of an expression. So we have 4 here, and that's the last index that will be updated, because after 4 you will be updating 8, which does not exist in this tree, right? So this is your BIT. Finally, it's done. BIT constructed. Prefix sums are over here. All you need to do is go for every S of I and find out the corresponding S of J's that you can have. So S of I initially is 1. What are the possible S of J's that you can go for? I think we said 5 to 8 is what we want. So S of I equal to 1. From 5 to 8, we want all the frequencies. I mean, the sum from this BIT in that range 5 to 8. So this is what you do. From 5 to 8 is what we want. So again, BIT asks you to take effective indexes. So this becomes 6 to 9. Okay, 6 to 9 now. For this BIT. Actual range is 5 to 8. 6 is this node. All you need to do to find the sum from 6 to node 0 is go up the parent all the time. Okay, and to go up the parent, you need to use the exact same formula, except that there's going to be a minus here. Okay. If you look at this, actually what's happening is you're setting the rightmost bit to 0. This is actually taking the entire number, removing all bits in that, setting everything to 0 except the rightmost bit, this number here. Right, so taking the 2's complement and all that is just so that we can set the rightmost bit to 0 after we subtract it. So what we're going to do, rightmost bit set to 0 gives you 4. That's the parent, like we said. So from 0 to 6, you'll have a sum of 2 plus 4 plus 0, which is, I've run out of space again, but yeah, I think there's some space here. So 6. From 0 to 9, oh god. Is 9 really going to appear now? Oh god. Okay. Nothing to worry about. So when you add indexes 8 and 9, thankfully 8 is updated all the time. One reason is because it stores all the indexes from 0 to 7, all the sum of the indexes from 0 to 7. So I could just put in a 6. But you can also see that if you use this formula, it will turn out to be 6. And I clarified that. 9 is never updated, it's 0. Okay, and when we say from 6 to 9 is what we want, what we are saying is that sum of all elements up to 9 minus sum of all elements up to 6 minus 1. Nothing fancy here. We want to take the element 6 also. This is inclusive, right? So that's the reason why we are removing all elements before 6, which is up to element 5. So this had gone wrong. We don't need to go from element 6, we should go from element 5. That is 1 plus 4 plus 0. So this is 5. This is your previous sum, I mean left worthless element sum. And the other sum is up to 9. So 0 plus 6 plus 0. So this is, what's that? This is 6. So effectively your sum here is equal to 6 minus 5, which is 1. So the elements falling in the range for 1, the S of j is basically is 1. There's just one S of j, which is this element 5. Okay, one element in the 5 to 8 range is this element. Now what you need to do is, because these elements have been already counted, you need to remove this 1 from your BIT. So that will be an update operation. Again, you'll come here, you'll subtract this by 1, and you'll find out all pairs which have to be updated. So that will be, this will become 3 and this will become 5. Okay, so this element has now been discarded from the BIT. So the next element is 5. 5 tells you that you have the range from 5 plus 4, B was 2, so 5 plus 4 is 9, inclusive 9, comma 5 plus 8, which is 13, exclusive. Now this range never occurs, so I won't be looking at this, but the program will work for this also. Exclusive with 5 minus 8, nah, that's just 0, exclusive 0. In fact, this becomes inclusive now because you're going up to 0. 0 is fine. What about S of I? That is 5. So exclusive of that. So this becomes inclusive. 0 to 4. Now this time I won't forget. BIT has the range from 1 to 5. And because we want this index also, we're going to be setting it to -1 of that. So that's 0. BIT of the first 0 elements is 0. That's cool. 0. And this will be subtracted from BIT of first 5 elements. So that is 1 plus 3, which is 4. This is equal to 4. Now, logically, of course, you see that 5 can match with these 4 elements to add 4 to the sum. So till now we have from the first element, this one, we have 1 in our answer. And now 5 has just contributed a lot. It's given us 4 elements. So 5 gets out of the way. 1 comes in. 1 needs a range from 5 to 8. So we go through the same procedure again. I'm sorry, 5 has to be updated, right? So 5 has an effective index of 6, and you update the nodes basically. So 6 is turned into 1. What's the next node after 6? 8. This becomes 4. Okay. Yeah. So now we come to 1. 1 finally, like we said, it's this value from 5 to this value up to 6. Oh no, I'm sorry. Up to 9 is what we want. So from 5 to 9 is what we want, right? So this is 4, and this now has become 4. So that is effective contribution of 0. Plus 0, plus again there's a 1, so this element is removed. 1 is removed, meaning that this becomes 1, this becomes 2, this becomes 3, and that's it, yeah. That's all that we have. So now we have another 1. So again the same thing happens. We get 1 plus 2, which is 3, and we get 0 plus 3, which is 3. So effective contribution again is still 0. So this node is now kicked out. We give this a score of 0, score of 1, and score of what, 2? Yeah. Now this node, effective index 3. No, in fact, I need to find the ranges for this guy. So finally, almost done now. The ranges are 2 plus 4, which is 6, and 2 plus 8, which is 2 plus 4 is 6, 2 plus 8 is 10, yeah. So this is completely out of range. That's nice. This one, 2 minus a huge number, so this is 0, inclusive. 2, so inclusive will be 1. The 0 to 1 is what we want here. We won't be finding any, but let's just check that. So all elements up to 2 in this Fenwick tree. So up to 2, which is here. 0. Cool. Kick out this element. Effective index of 3 gives you a subtraction by 1, gives you 0. 3 has its next node equal to 5, if I'm not mistaken. I certainly hope I'm not mistaken. So 5 has the next node as 6, which becomes 0, and 8 has the next node as 1. Okay, and now you see what's happened to the entire tree. From 0 to 4, you have some number, but everything else has been set to 0. And 0 to 8 also, of course, because that's just addition of this. So 3 is the only guy remaining. There's absolutely no one else in the tree remaining, apart from 3. But even if you run this on the number 3, you'll get 7 and a pretty big number. Both of them out of range, so you don't need to take care of that. These two ranges, that becomes 0, again, because of the pretty big number, this becomes inclusive 0 with inclusive 2 instead of 3. So inclusive 0 with exclusive 3 becomes inclusive 0 with inclusive 2. 0 to 2 is what we want. Again, all elements up to the value of 3. Okay, because the 0th element also has to be counted. So all the elements up to the value of 3, we have 3 here. We have 0, 0, 0. Perfect. This is 0. So finally we have 5 elements for this bit position which are contributing to adding 1 to the bit at bit 2. So because these are odd, the bit at position 2 is 1. That's a guarantee. Okay, that's there. And let's just see if that is the case. What are the possible sums for this? I'll just write them down. So I can just take these elements in the array. So that's 1, 5, 9, 10, 11. For the second element, there is 4, 8, 9, 10. For the third element, there is 4, 0, so 5, 6. For the fourth element, 0 is not being counted, that's being ignored. We have 1 and 2, and for the fifth one, we have this. So these are the sums that we have for this bit position. Now the question had said that we need to XOR these sums. So let's XOR them. 9 and 9 will cancel each other out, 1 and 1 will cancel each other out, 4 and 4, 5 and 5, 10 and 10. Now this is great. 6 and 2 XORed will give you 4. Okay, so anyway, we'll get to that later. 1 XORed with 11 will give you 10. 6 XORed with 8 and then XORed with 2 will give you 8 plus 6 plus 2, which is, 6 and 2 XORed will give you 4, so this becomes 4. 8 plus 4, which is 12. Alright, these two numbers now need to be XORed. So that becomes 8 is cancelled from both, so that becomes 2 XORed with 4. Yeah, this is what we have. So that would be 6. So this is the effective thing. And at bit position 2, you see that this is the bit position 2 and it's set to 1, just like we said. Alright, we have, I hope we have proven it convincingly that this technique works. We can use the binary index tree, and the complexity for actually building this is going to be n log n in terms of the number of nodes that you have. So the number of nodes that you can have at most is 1.5 into 10 raised to the power 7. That's a lot of nodes. And log n multiplication, whatever you have here, that is about 15, so that will be 24, yeah. Not log of 24, but 24 itself. So this number will be pretty big, but it should fall within the time complexity requirement of this question. The other thing that you need is to find the sums for every possible number in the prefix array. So that is just n into log of this binary index tree, the size of this tree, the number of nodes actually. So that will be log of size of the tree. This is smaller than this value, so we'll ignore this. What does this come out to be? 24 into this value. So that's 3 into 12, which is 36. So 3.6 into 10 raised to the power 7. That is about 3.6 seconds of computation. The time requirement for this question is 4.5 seconds. I mean, anything under 4.5 seconds should be accepted. So this solution should be accepted. So that is Barron's or sums. Tough question, I would say, because I don't know how we can ingrain in ourselves the feeling that we can find corresponding SFJs for all SFIs. Maybe through practice, but importantly, we need to find ranges here. But even before that, we need to think in terms of binary. We need to look at the question, understand what they want. They want the XOR of all the sums. So it's stuff like this that allows you to think in terms of binary and then come up with prefix sums because they're asking you for sums again. And then, of course, comes the really hard part of mathematically constraining the sums that you can to a binary index tree. I found the binary index tree quite useful, so I might make a tutorial on that. You could subscribe if you want a notification. If you have any doubts on this question, please feel free to write your comments below, and I'll be sharing the code for this very soon in the description below. So until next time, thank you.